Okay, welcome to my third and final part to my cosmology lecture. This is for Cabrillo College, Astro 4, and this is our chapter 23 from the text. But actually I put this together myself without really much reference to the textbook because I don't really need the textbook for this. I know this stuff pretty well. Okay, so where we left off last time was the universe looked like it was at critical density, and so we talked about how that is favored. Our favored theoretical notion for the universe should be critical density, because that is a universe that has exactly zero total energy. Maybe I should pause on that for a moment. You might say, what? Zero? This is not zero, Rick. You would actually, well, in some sense, no, it's not zero, but it is zero in the mathematical sense, because it turns out that to have our most favored, most convenient of all physical principles, the conservation of energy, that in local or even cosmic context, you need to include the gravitational potential energy as a negative. Okay, so gravitational energy is an attractive force that actually provides a negative, so that you can convert that into a equivalent positive energy, like kinetic energy, as it gives up potential energy, and therefore energy is conserved in that kind of a system. You drop something and it speeds up, so where does it get all that energy? Well, in order to have conservation of energy, it must have already had that energy. It just had it in so-called potential energy form. So this is something we already talked about in chapter 4 and 5, but I thought it was worth restating now. So if you have a universe that is expanding but also self-gravitating, and if it's exactly at the critical density, then those two energies are in balance, and actually the universe has zero total energy. We know how to create such a universe out of nothing, just by using the laws of quantum mechanics. So we've always favored, at least theoretically, or hoped, or I don't want to sound like we're cooking the answer before we know what it is. We've just always had kind of a we've always been rooting for a zero energy universe, or at least many of us. I suppose it would be even more interesting if it turned out not to be, and then we'd have more mysteries. But those mysteries would really, those mysteries are almost more mysteries than we want to deal with at the moment. We've got enough mysteries. We still want to know what the dark matter is. We want to know really what the dark energy is. So we've got enough mysteries. Frankly, most people, when we saw that the universe was at zero density, were somewhat pleased, that we live in a universe that obeys the kind of simplicity that, is beautiful. And physics has been very good at finding answers that turn out to be right by following our sense of beauty. Okay, so we're ready to move on. This is the slide that we looked at last time, so let's move on. Now, we saw our first map of the cosmic background radiation, and it looked pretty smooth, except there was a clear bipolar or dipole field to it, which we accounted for by simply the fact that the Sun and the Earth, too, are moving relative to the entire observable universe. And that's because it just so happens, by random chance, that we have a lot of galaxy clusters and superclusters more on one side of the sky than on the other side. And that has acted over time to slowly accelerate us up to about 600 kilometers a second relative to the universe, well, the observable universe as a whole. Okay, but now we're going to ask a different question, and that is, are there any other fluctuations in the temperature of the microwave background on a much finer scale? So what we did is we... Okay, wait a minute. There we go. So we launched a new satellite mission, much better technology. It's called the WMAP, the Wilkinson Microwave Anisotropy P. What was the P? Probe. That was it. WMAP. Okay, so it rolls off the tongue nicely. And this is what it saw. So all this fine scale gray structure that you see, this is all due to the small scale fluctuations in the temperature. And I hope you can see that they exist on really on all scales as near as you can tell. Now forget about the red. The red is just foreground microwave emission from interstellar clouds and giant molecular clouds that we talked about before. So those are still there, and those still have to be removed. Removing those from the data is challenging, but it's doable. And so they're clearly identified, and they are pulled out. Pulled out at least figuratively. They've been left in on the map, but they're different colors. So what we want you to focus on is just the gray. And you can see some large areas of gray that are a little darker, and you see some large areas of gray that are a little lighter, and you also see medium scale things that are larger, that are brighter, and some that are dimmer, and those very fine scale things that are brighter and dimmer. So it looks like there is structure, there is lumps in the microwave background which would correspond to lumps in the matter distribution on all scales that we can see on this map. Let's take a look again. Let's look at an all-scale, all-sky map, and now we're going to color-code it to make it all a little more obvious, and I think you can see that there's lumpiness on all scales. Pretty big scales, and also pretty small scales, about the limit that this satellite technology could detect. So let's take another look just to... trying to take a sphere and flatten it out is kind of challenging, so here's another way that might be a little more intuitive. Let's go ahead and let it be a sphere, so there's no distortions now in how you lay it flat. We're not going to lay it flat, we're just going to photograph the two sides of the sphere, and so you get a 3D kind of impression looking at this. And again, though, the result's the same. You see structure on all scales. Now what you can do is you can ask, okay, how strong are the fluctuations, and on what scale? So 90 degrees, well, that's a quarter of the whole sky. That's the biggest scale you could hope to have any data on. 0.15 degrees, well, that's tiny. That's about the size of, a lunar Maria as seen by your eye. It's barely at the resolution limit of the naked eye. Okay, so that's pretty small. And what you see here is a curve, and the curve has lots of wiggles in it because of what we call acoustic vibrations, acoustic oscillations, that I don't really want to spend a lot of time trying to explain because it's a little too wonky. But I will say just that the prediction of inflation, which we have introduced now, the predictions of inflation follow the simplest model of inflation. Okay, you can cook up all kinds of more complicated models that have less beauty to them. They're not as simple. That would be different. But the simplest model of inflation, which has just one free parameter, obeys pretty darn well the data. Now the data still has these error bars. You can see the size of the error bars is. So it looks like, maybe we could do better. Maybe we could do better. So we designed and then we launched another mission called the Planck mission, and it had even better quality data. So I like this slide because it shows, first of all, the satellites themselves. They all look pretty different. And the technology, so the Planck mission was launched in the late 1990s, I think. And WMAP was more like the early 90s, and the COBE was 1980s. Designed in the very early 80s. So COBE, you couldn't see any of the small scale structure. The technology just wasn't good enough. But WMAP did, and Planck sees it much better. So here, this little man-like figure here, without a head, or maybe he's got a head, looks pretty fuzzy. Here, it breaks up into a lot of smaller scale features. So the Planck mission was a definite improvement. And now let's compare that again to the fluctuations And now we're going to put fluctuations in terms of temperature here. And this is in micro millionths of a degree Kelvin. Temperature fluctuations, this is squared per, and it's microkelvins squared. The reason is because they go positive and negative, and we want to square them so they're all positive, and so it just plots a little better. You could plot it in different ways. But look at this. The error bars are still here, but you can't see them. The error bars are so tiny on these large scales because there is such a large sample. There's so many bits of this all-sky picture that are as large as 0.2 degrees across. That's pretty tiny. Remember, the moon's about a half a degree across. That's about right here. How many full moons would it take to paper the whole sky? Well, a decent number of them. And so there's pretty good data, and so the error bars are so tiny that you can't even see them. And it fits perfectly. I mean, this kind of data just brought all kinds of delight to the cosmology people who designed and executed this mission, and then compared it with the simplest models of inflation. Now you might say, well, what about over here, Rick? The error bars now get pretty darn big, and even the inflation predictions get pretty darn big. So the uncertainties there get pretty big. So what's that about? Well, what that's about is it depends entirely on what we call cosmic variance. So it depends on where are we in the universe. How many 90-degree across blotches of area are there across the sky? Well, about, not many, like 4 pi. Not 4 pi, less than 4 pi. Anyway, there's just a small handful of them. So of course you're going to have uncertainties, and those uncertainties cannot be removed. They cannot be removed, ever. We are where we are in the universe, and that's the way it is, and that's the way it'll always be. So this is so-called cosmic variance, and these error bars cannot be reduced, and even the error bars in the inflationary predictions themselves can't be removed, again, because there's just too few. Because we're at a given place and the universe is lumpy on all scales, even very big scales, and we can't reduce that. Okay, we can't just, if we could move ourselves around magically throughout the entire universe, not just the observable universe, but all of it, then you could hope to beat these down, and maybe they would follow the blue curve here. Certainly looks like it would. Look at how good that agreement is. That is just stunning. So after the Planck mission, the amount of the energy density, matter energy density of the universe in the 3 main components shifted around a little bit, not a whole lot, but a little bit. So now it looks like in terms of dark matter, we have just a little less than 27%. The ordinary matter, what we used to think in the old days was everything there was, all the stuff that makes up stars, you and me, planets, interstellar clouds, all that stuff, that's 5%. A tad less than 5%. And the dark energy is almost everything else, over 68%. So here's lumpiness in the universe. On rather small scales, 10 million light years, that's about the size of a pretty rich cluster of galaxies, pretty big cluster of galaxies. Then the lumpiness is, clusters of galaxies are lumpy. They're pretty obvious on the sky. But when you get to bigger and bigger scales, now 100 million light years, now 1,000, that's a billion light years. Now you're talking about, a tenth of the size of the observable universe. And the universe gets smoother and smoother. And look at how smooth. I mean, this is a log scale. So density fluctuations from example to example damp out. And so on the largest of all scales, we still think the universe is very, very smooth. But cosmic variance means that there's still some lumpiness on even the scales that we can see, and so there's big error bars here. But on small scales, it's pretty darn tiny, and it agrees pretty well. Okay? So the conclusion is that the density parameter, which we often designate with the Greek letter omega, of the universe is 1.0. So what is omega? Omega is just the density of the universe in terms of matter and energy divided by the critical density. So to say it's 1.0 is to say that we're at critical density. That's exactly what is predicted by inflation. The spectrum of the strengths of the density fluctuations is a power law with a slope of -1 in real space. And that's also what's predicted by inflation. Now there's a small little break in that that's due to the fact that there is a preferred scale in the universe. It has to do with the Planck distance. But let's forget that for the moment. This is forgetting about that for the moment. It's a tiny little thing. Let's not obsess over it. The slope has the right slope, okay, predicted by inflation. The acoustic peaks in the WMAP and the Planck power spectrum follows all the wiggles predicted by inflation. It follows them perfectly. So it's looking like inflation, and in its simplest form. I mean, that's what we really like. We don't need to cook up some artificial kludgy version of inflation, because then it looks like you're just cooking the books to try and make it look right. It doesn't have that clean feeling to it. You'd like to think that you don't have to contrive. That's the word we used back in chapter 0 when we talked about scientific method. So we don't want to feel like we have to contrive things to try and make them agree. So when inflation in its simplest form with only one free parameter agrees with everything we see, we feel that, wow, I think this is actually right. Now, some philosophers get all bent out of shape about, well, you haven't proved it. The problem is that I don't think they understand the difference between the idea of proof in a closed logical system like mathematics and in a very open system like the nature of the universe. So I'm going to rephrase something that we talked about in chapter 0, and that is, in a closed system, yes, you can do proofs because you define the system. You define the axioms, you define everything within it. And within that, then yes, absolute logic is closed, and so it is possible to do proofs and disproofs if you're clever enough. But the universe was not made for us, by us. We wake up one day when we're 2 years old and we look around and there's a universe outside of our skin, and it's up to us to just make sense of it. Okay? And I'm totally comfortable with that, and most good scientists are totally comfortable with it. It's the darn philosophers who get in the way. I will tell you that those in science that I know, and myself included, we frankly disregard just about everything that the so-called philosophers of science, a very highfalutin term for people who I think are out of their depth. They don't know what they're really dealing with. And when you're talking about the real universe, it's perfectly acceptable and it's perfectly correct that there should be some remaining uncertainty. Okay? We don't have infinite technology. We don't have infinite time to figure everything out. There's going to be remaining uncertainties. So, anyway, that was a little diversion. I'm going to pick things up again here. So, why is it that inflation happened? So, a leading contender is the idea of symmetry breaking. So, and this is maybe the simplest one to try and make a little sense of for beginning students. The 4 forces of nature. 4? Why 4? Seems like an odd number. Why not 1? 1 seems more natural. Could the forces of nature really be unified if we just look carefully enough? If we just look at high enough energies, when all of the forces could possibly have been unified into a single force? It's kind of a beautiful idea. We don't know whether it's true, but it's at least an interesting idea that actually has borne a little bit of fruit already so far. So we do have some progress here. It turns out that the weak force and electromagnetism, so this is obviously one of the 2 really weak forces in nature, and then the electromagnetism is one of the 2 really strong forces in nature. And it turns out that these 2 forces were unified at an early moment in the universe when it was less than 1/trillionth of a second old. The temperature was so high, the energy was so high, that in fact the weak force and the electromagnetic force could be unified and described by a single force called now the electroweak force. And the predictions of that are the W and Z bosons, which have been found in particle physics experiments. Those are at low enough energy, they're not that low, but they're at low enough energy that they are accessible by our highest powered particle colliders, trying to smash things together at high enough energy that, according to the laws of quantum mechanics, just about anything that is accessible at those masses should be produced. And if you look long enough and hard enough and you run your experiment long enough, you should see them. And indeed we do. So we now believe the electroweak force really was a single force that then split into the electromagnetic force and into the weak force after a trillionth of a second. Okay, so that's encouraging. Well, maybe we could unify the strong force into that as well. Unfortunately, that would take a particle accelerator so far beyond anything either financially or technologically possible that we're not going to be able to do it. The only hope that you might be able to come up with something like that is through pure logic, and maybe to look for extremely high energy places in the universe, like maybe the black hole at the center of our galaxy, or or hypothesized primordial black holes in the early universe, to have done the experiments for us and to look for something like that. But the prediction, one generic prediction of a so-called grand unified force, the simplest grand unified forces predict that the proton should not be stable. It should have a finite lifetime, in the same way that the neutron all by itself has a finite lifetime. Neutrons, when you take them out of the nice, comforting, stable, cozy little places that they occupy inside the nuclei of atoms, if you take them out and you leave them all by themselves, they can't handle it. They cannot handle it. And after 11 minutes on average, they just fly apart into a proton and an electron. Electrons, we believe, are totally stable. Protons, we had always thought, well, maybe they're stable, but then with the grand unified theories which were being devised early on, the prediction was that the proton should decay after about 10 to the plus 32, 10 to the plus 32 years. And I think I talked about this earlier as well. Well, how could you possibly test anything like that? The universe is only 10 to the 10th years old, Rick. 10 to the 32 years, that's a long time to wait. But since it's a quantum process, it's really only a probability per unit time, and therefore all you really need to do is to get 10 to the 32 protons all together inside a detector that could detect whether any single one of them decays. 10 to the 32 protons, you can do the math. Turns out that's actually an accessible amount of stuff. It's big, it's many, many tons, but it's not unachievable, and we've achieved it. So in the Sudbury neutrino detector, it turns out there's enough water that we can actually access, that there's enough protons in there that we can test that, and in fact we see that the proton is indeed stable. In fact, it's stable to at least 10 to the 34, and maybe they're even starting to push it up to 10 to the 35 years. I don't know what the current limit is. 10 to the 34th, I think that number is a few years old now, so they might have been able to get that up a little bit higher. So that's 100 times longer than the simplest grand unified theories. So we don't have a grand unified theory of physics yet. But if we did, at least in general outline, it might look something like this in terms of the evolution of the universe. So you start out at the Big Bang, and maybe there was one single force. We'll call it the Force. Why not? Everybody loves Star Trek. Star Wars. Not Star Trek. I guess we love Star Trek too, but Star Wars, yes. Obi-Wan Kenobi, the Force. May the Force be with you. At 10 to the minus 43 seconds, the temperature is 10 to the 32 Kelvin. Particle energies that are being created and destroyed at these kind of temperatures are 10 to the 19th billion electron volts. As the universe expands and cools, it follows this track, and then gravity would separate out. That's at least the idea, maybe. None of this is proved. It's speculative. It's sort of beautiful in a way, but it's uncheckable. The only thing we know for sure that actually happens is down here, after a trillionth of a second. So the electroweak and the electromagnetic split to the weak and electromagnetic forces, that we got confirmed. But we don't have this yet, the strong force, and then gravity coming out. Now gravity is an extremely weak force, and it separating out from this probably would not have been a big deal in terms of energy in the universe. However, this split, which would happen at a time around 10 to the minus 33 seconds or so, that would be a big deal because this is the strong nuclear force. That is a very strong force. And that's electromagnetism, and that is a very strong force. These are comparable in strength. They only differ by about a factor of 100 in strength. Okay? So that would be a big deal, and that could have added enough energy to space to have generated inflation. A negative gravity to space and generated inflation. At least that's a possibility. Okay? So gravity would freeze out first, but it's the weakest force and therefore would not be a big deal. Then the strong force would freeze out of the so-called grand unified force. And that separates the strong and electromagnetic forces. Those are the two big forces in nature. The energy liberated by these two could perhaps have powered the inflationary epoch. There's other ideas, even wilder and more speculative so far. Inflation is bizarre, but actually it's a totally logical outcome of well-tested quantum physics, and it's passed its first tests. Again, the simplest model of inflation is the one that works the best.